Welcome to our undergraduate research competition presentation. We will present an AI and computer vision based robot teaching assistant that we like to call Reacher. Now, as part of the fourth industrial revolution, artificial intelligence is expected to play a major role in education. However, an issue with the currently existing technologies is that they are usually very focused on a specific task, and there's a lack of solutions that can take over major duties of a teacher or a teaching assistant, especially in a pandemic scenario as currently ongoing. Now, as we're gradually returning to face-to-face delivery, there is a clear need for reducing contact between faculty and students to reduce the spread of COVID-19. Our solution for this is Reacher. Reacher is a fully fledged robot that automates many of the major duties of a teaching assistant using computer vision or artificial intelligence. Now, our motivation for creating Reacher were its role in combating COVID-19, its role in the advancement of AI in education, and our desire to create a solution that is marketable and is useful even outside a pandemic. My colleague Yazid will now demonstrate our subsystem overview.
Thank you very much, Sharif. So our robotic teacher assistant Reacher primarily functions by replicating the tasks of a teacher assistant. For our project, we highlighted some of these tasks, which include proctoring of face-to-face examinations, collecting exam papers from students, interacting with students to provide academic support as well. And to achieve these tasks, we built 5 major subsystems. The first one is a system for cheating detection, another subsystem for navigating a classroom autonomously, a subsystem for the contactless examination submissions, which is vision-based, a human and robot interaction or voice interaction subsystem, and a subsystem for providing personalized content to students. So current online examination platforms include using a hybrid of AI and human proctoring. These softwares use simple computer vision techniques, such as the detection or the absence of faces in a certain scene. Moving on, our proposed cheating detection subsystem includes the use of 4 cameras that are set up at different angles on the robot. The video footage from those 4 cameras are uploaded to a computing server. Then we use deep learning algorithms that have been trained on collected data to predict whether there has been cheating or no. A report of the instances of predicted cheating along with the video footage can then be reviewed by the instructor. Some examples of cheating are the use of mobile phones. Reacher recognizes this by detecting phones in a frame. Another one is the passing of cheating material, which is recognized by the detection of extended arms.
Thank you, Yazid. Now, the robot needs to be able to navigate the environment autonomously while avoiding collisions. So for the navigation, we'll be using the ROS framework, which provides many useful tools specifically for robot simulation and real-time visualization, as well as many packages from the ROS navigation stack. This ROS navigation stack provides an abstract implementation of intro localization. First, we need to provide the odometry data from the motor encoders and the gyroscope to calculate how much the robot has moved from its original position. Using this, the robot would first need to be manually driven around the environment, and the SLAM algorithm, such as G-mapping, would be used to create a static map of the environment using a 360-degree LiDAR sensor. Next, we need to localize the robot, and although the odometry provides some degree of localization, has some errors, and these errors get added over time. So to compensate, we are using the adaptive Monte Carlo localization. And as you can see here at the beginning, there are many arrows or guesses being made by the algorithm, and they vary widely. But as the robot is driven around, the data from the LiDAR is constantly being compared to the static map, and it is being adjusted accordingly, resulting in less variation between these guesses. And finally, we have autonomous navigation. We can send goal points, and the global planner uses a static map to calculate the route to the destination, and the local planner uses a 3D sensor to avoid dynamic shifting obstacles. We are using a 3D sensor because it provides additional height information, which would be useful in detecting the legs of the tables and chairs in a classroom. And now my colleague Abdul Rahman will explain the paper scanning subsystem.
Thank you, Razib. Now, I will talk about the vision-based scanning subsystem. For our robot to be able to serve as a complete teacher assistant or replacement, it is essential that it has some way to collect exam papers from students after they finish their exams. This is even more complicated nowadays as collecting physical papers carries a risk of transmission of disease. As such, we came up with a system to scan the exam papers of students using high-resolution cameras. This kind of solution comes with a few different challenges that need to be solved, such as properly detecting when an exam paper is being shown to the camera, when to begin and end the scan, how to extract individual pages from a video stream, detect the borders of the pages, crop and de-skew them, plus any post-processing to make them look properly scanned. This kind of solution already exists in some form on popular scanning apps on smartphones. However, our system would automate all these tasks and would make them transparent to the user, a clickless, vision-based scanning system. At the end of an exam, students will walk up to the robot, ready for scanning, 1 to 4 at a time. Instructions will be displayed on a screen. They will each hold up their exam papers to one of the 4 cameras on the robot and quickly flip through their exam papers, a video of which will be saved and sent to the server for processing. The system will detect QR codes on the pages to start and stop the scan. The system scans all the frames, calculating and storing all the relevant metrics. It then extracts the best frame from each page using these calculated metrics. Each page is processed to turn it into a final scan. All the pages are adjusted, collated, compiled into a PDF, and then a copy is sent to both the student and the teacher.
Thank you, Abdurrahman. For the human-robot interaction, we first created the wake word "Hey Reacher" using the Porcupine Hotwood detection engine. We use this primarily because of its high accuracy and low power consumption, which is quite important considering it's going to be constantly listening. The student would then ask a question and the audio would then be synthesized to text and be sent over to Dialogflow for natural language processing. Dialogflow provides easy context management through the use of state charts, and the response is then sent back to our Python backend server via webhook. Depending on the question, the backend server would then query to a recommender system, after which the text is then converted to audio using Google's text-to-speech API. The user would then be presented the relevant info through a web browser on a tablet running Ionic. Here is a demo. Hey Reacher, I just don't get random forests and naive bays.
Give me a moment while I gather all relevant info about random forests and naive bays.
Now, the course material recommendation. These days, recommendation engines are used by many companies in many ways, such as recommending categories of news articles based on freshness of content, or recommending movies and TV shows, such as by Netflix. In our robot, we use a recommender to return to a student the content that they will most prefer from a list of relevant course material. This subsystem is divided into 3 sections: content retrieval, content personalization, and profile generation. Content retrieval. When a student makes a request, the context of that request, such as the topic, is determined by Dialogflow and is piped into a content retrieval system. Now, the content retrieval system returns a list of the relevant content based on the parameters from Dialogflow, and then passes this list into the content personalization or the recommendation engine for content personalization. Now, content personalization. Reacher generates a profile for each student that interacts with it. But like in the first interaction, there will be no profile for that student. So if there is no profile for a student, a default profile is used, which makes use of a simple popularity recommender to return to the student the highest rated content among the list of the relevant course content or relevant materials. If a profile, however, does exist, then Nature utilizes both content-based and collaborative filtering, utilizing to recreate, to return to the student the content that they will most prefer based on the student's history, the student's previously highly rated material, and other similar students' preferences.
The means used for identifying students is facial recognition. Reacher will firstly detect any face that is present in a frame. As soon as it detects a face, it will capture an image and extract the facial features of that face. These features are compared to the ones that are stored in the database. In case a match is found, it will directly access that student's profile. In case a match was not found, as can be seen in the bottom left image, then it will generate a new profile for that student.
Alright, all of our 5 subsystems are integrated together to form the robot teacher, Reacher. I will now briefly talk about the hardware design of the robot, some of which is exclusive to one subsystem and some that is shared between them. We use the Eugen Kobiki Turtlebot 2 as a base upon which to build our robot. We modified the base to better fit our needs. We mounted the Orbeck Astra 3D scanner along with a Slamtech RPi LiDAR unit to help the robot navigate. We used 4 Logitech high-resolution cameras and a generic Android tablet for display mounted on top of the robot. A laptop running Linux serves as the brains of the entire system. In conclusion, we set out to make an AI-powered robot teacher capable of autonomous proctoring, contactless exam paper submission, as well as support voice interactions for content retrieval and general conversation, all powered by AI. Other education AI solutions already exist, but they are focused on a specific task. Reacher satisfies the need for a comprehensive solution that can be used to mitigate the spread of COVID-19, but can be deployed outside of the pandemic as well.